this session. So we are gonna learn about Prism, optimizing key-value store for modern heterogeneous storage. So the talk will be delivered by Yongju Song from Sungkyunkwan University.
Excuse me, give me a second. Oh. Yes, thank you for the introduction, and hello everyone. My name is Yongju Song, and I'm from Sungkyunkwan University. I'm very happy to be here to present our work Prism. This is a joint work with Professor Uki Kim Sumit, Professor Chang Woo Min, and my advisor Professor Young Kom. As we all know, it is very common in storage systems to employ various types of storage devices for cost efficiency. Traditionally, storage systems have adopted a hierarchical approach, and this approach simply categorizes storage devices into performance and capacity devices. In the past, SSDs and hard disk drivers generally served as performance and capacity devices, respectively. And now let's shift our focus to the modern storage devices. As technology advances, high-performance non-volatile memory and high-bandwidth SSDs are potentially replacing traditional storage solutions. In our work, we explore whether traditional hierarchical storage architectures are still effective for these modern storage devices. Here is a table summarizing the performance characteristics of the widely used storage devices. When we consider storage devices based on their capacity, price, and read-write latencies, we can see that they can generally be categorized as either performance and capacity devices. However, what if we add the criteria of bandwidth and endurance for categorizing? Then we can find out that it is difficult to simply separate into two types, unlike in the past. And practically, NVMe is great for endurance and read-write latencies, but flash SSD offers much higher I/O bandwidth than NVMe. So let's take a quick look at how heterogeneous storage system works in today. In the case of performing write operations, as we see in the table before, NVMe has limited bandwidth, so the system could face a bottleneck when storing bulky data. Moreover, due to this bottleneck, some SSD resources may go unused, leading to a loss of efficiency. For read operations, the system needs to traverse each layer from top to bottom, so it can lead to wasting CPU cycles. Additionally, if the data we are looking for is stored on the SSD, due to its slow latency, SSDs can degrade the overall system performance, particularly tail latencies. So our research question is, how should we design a heterogeneous storage system in the modern storage landscape? We answer the question by proposing a novel key-value store, Prism. First, Prism leverages strengths of each individual storage devices to compensate for their respective disadvantages. By doing so, we can achieve high performance and cost effectiveness together. Second, as storage performance continuously improves, the CPU has now become a new bottleneck. To address this, Prism aims to minimize software stack overhead, thereby achieving high scalability. Lastly, Prism consists of 5 components that are scattered across multiple heterogeneous storage devices. So achieving a efficient crash constancy and concurrent control for scattered devices is an issue of importance. Now let's dive into the details of PRISM. Basically, PRISM has 5 components that utilize DRAM, NVM, and SSD. The first component is the persistent write buffer, which provides a fast path for accessing recently written data. Next, we have value storage component. Value storage is designed to handle the larger I/O and utilize flash SSDs for high storage bandwidth. To avoid high latency from SSD read, the scan-aware value cache component caches read-hot values. Caching is conducted from only the value storage component. The persistent key index is responsible for mapping a key to the location of the corresponding value data, providing efficient and fast access to the value location. Finally, the heterogeneous storage index table. It is a kind of an indirection table that manages the location of value across the scattered storage devices, providing a unified view of the data to the users. Here is an example of an insert key K1 and value V1 operation in PRISM. At first, PRISM writes the new value to the PWB. PRISM then infers the persistence of the value data and updates the HSIT entry with the location of the new value in the PWB. Finally, PRISM inserts the key with the address of the HSIT entry to the persistent key index. Later, the PWB space utilization reaches the threshold. PRISM has to migrate the value data to the value storage. At this point, PRISM utilizes the technique called asynchronous bandwidth optimized write to achieve high bandwidth of SSDs and prevent application thread blocking. First, when PWB utilization hits the watermark of 50%, the up-to-date values in the PWB are asynchronously written to the value storage. To optimize performance on SSDs, PRISM writes values to value storage in fixed size chunks of 512 kilobytes. This is because large sequential writes are more efficient for SSDs. Additionally, while reclaiming PWB, an application thread can write values to the rest of the PWB to ensure that data migration does not negatively impact system performance. When performing a lookup operation, the most critical case is reading value data from value storage. To enhance SSD read performance, we designed opportunistic thread combining scheme. It dynamically determines the I/O batch size and to utilize the high bandwidth and mitigate the high latency of SSD. PRISM manages a thread combining queue, which is virtual queue, and this is for queuing threads requesting read operations. And a leader thread collects its own and followers' read requests. Then leader thread submits the batched request when there is no more followers or it reaches to the limit of the I/O batch size. Lastly, let me introduce how the PRISM system ensures cross-media crash consistency and how to access the up-to-date value data. Here is an example of insert key K2 and value V2. When a new value is written on PWB, it is first stored with the backward pointer, and then each forward pointer is updated. If the backward pointer and the forward pointer in the HSIT entry are well coupled, the value is valid and up-to-date data. Similar to the insert process, when updating value data, PRISM first assigns a backward pointer, then updates the forward pointer to invalidating the old forward pointer. This protocol ensures crash constant update of values on PWB and value storage using HSIT. We evaluated our Prism on 2-socket machine. Each socket has 6 Intel-Optane DIMMs and 8 of Samsung 9080 SSDs. For benchmark tools, we use YCSB workloads and compared with KVEL, Matrix KB, and RuxDB. We also allocate their hardware resources at the same cost for evaluating cost efficiency. In this experiment, we evaluated our Prism using YCSB workloads. Our Prism shows up to 13 times higher performance compared to existing systems. This is because Prism employs multiple write buffer and do not require level compaction, unlike traditional hierarchical storage systems. In addition, we achieved high read performance thanks to direct access using the HSIT. This figure shows the effect of opportunistic thread combining for read operations. TC represents our thread combining technique, while TA is a variant of Prism that uses fixed queue depth. With this scheme, Prism can adjust the I/O batch size and efficiently derive performance of SSDs. Especially, the thread combining technique delivers significant benefits in tail latency. For more detailed designs and experiments, please refer to our paper. And this is all I have. I will be happy to take your questions. Thank you.